Hey Code Websters, so today what we are going to be doing is we're going to attempt to understand the mystical land of neural networks with a bit of code and a lot of mathematical principles. Before we begin with the code part, let's try to understand the boring part. I meant the mathematical part. Neural networks are a system of nodes that take in a bunch of inputs and release corresponding outputs. The goal of the network is to transform these inputs into the correct outputs through altering the network's connections. Here, you should see a diagram of a neural network. We might change the number of nodes in our code, but it follows the same general premise. In a neural network, we have a set of input that we place in an array format. Each input has a weight associated with it. Basically, at Z1, we have a value of x1 multiplied w11 plus x2 multiplied w21. This is assuming a linear activation function. We'll get onto that in a second. While Z2 has x1 multiplied w12 plus x2 multiplied w22. As you can see, the weights define how much influence the inputs have on the output. Mathematically, we define the weight matrix as W equals like that, and the transpose of it is like that. We define the transpose so we can multiply it by our inputs and basically get an output matrix. So, as you can see, O1, which is classified as our output here, the first output, equals the transpose, multiply the input array. This goes through matrix multiplication, and it brings out O1 and O2, and our matrix actually follows the Z1 and Z2 that I explained before. From there, we have something called an activation function. The activation function can be any function you think of. However, we often choose the sigmoid function or the logistic function or the linear function for ease of mathematical calculation. I'm going to be using the sigmoid function. The activation function basically is acted on the transpose of the weight matrix multiplied the input array. Thus, our Z1 and Z2 become two different values. For our sigmoid function, or sigmoid activation function, our outputs are basically forced to be in between 0 to 1. So, mathematically, we show this as Z becoming the sigmoid of O1 before, and that transforms it into a sigmoid O1, sigmoid O2. From there, we have a second weight function. Let's define this as the V weight function, and this is from the hidden layer to the output layer. Since this is only one-dimensional, due to the output only having one value in this case, we'll define that as V1 and V2. Now, just as before, our output at Y, without the sigmoid enacted onto it, would be the transpose of that weight matrix V multiplied Z. And Z is our inputs in a way, but it's coming from the hidden layer. Now, this basically gives one line, and that makes sense because our Y value here is only one output and only has one node. This value is V1 multiplied sigmoid O1 plus V2 multiplied sigmoid O2. Notice the similarity to our first hidden layer output formula. Our input here are in essence Z, and our weight function is transformed in a way to V. Finally, we enact the sigmoid activation function on O2 to actually get our real output. Generally, the whole neural network can be mathematically displayed as Y equals the sigmoid bracket, V transpose multiplied sigmoid bracket, weight transpose times X bracket bracket. This can be further mathematically generalized by changing sigmoid to any activation function. Now, we will go and try to develop these formulas using Python. In our case, we're going to build a simple neural network that will get 3 inputs, negate the first 2 inputs, and leave the third as it is. So for example, we'll have 1, 0, 1, that will become 0, 1, 1. Now to develop any neural network, we'll analyze the key factors of a network. Our network will have 3 inputs, it will have 3 outputs, and we'll choose our hidden layer to have 15 specific nodes. So let's go ahead and head over to our actual Python file and actually calculate. So I've imported a few packages that you'll need to install. So you might go to install this, you'd go pip install numpy and pip install scipy to get all both these things, and these will be used in our actual calculations. So Now for Python, if you don't know anything about Python, I will be creating a simple tutorial later on. But right now, if you don't know anything about Python, go check up a website and see what you can do with that. But it's pretty self-explanatory. So let's go ahead and actually define this. So first of all, let's create a class. This will be our neural network class. Let's create a functional class to initialize it. Okay, now that I've written that out, let's try to actually understand what this neural network does. So we have our initialization here. We've got our input nodes, our hidden nodes, our output nodes, and our learning rate. I'll explain the learning rate when we actually train our data. Today, we will instead focus on trying to run through the neural network one time. The WIH that I define here is the weight matrix from the input layer to the hidden layer, while the WHO, World Health Organization, of course, is the weight matrix from the hidden layer to the output layer. Self.lr is the learning rate. The activation function, I've basically just created the activation function using a quick perk I like to use. I forgot the equal sign there. And I pass that through. And this basically sets up our neural network, which we'll be using in our queries. So let's go ahead and create a query. Okay, let's go ahead and try to explain this. But before that, I want to go back to our actual initialization, and I forgot to explain to you a pivotal part of our network. Here, we have numpy.random.normal, and we've got all these little parameters. You might not know this, you might not have used this, but I'll try to explain it a bit better. The 0 here essentially gives us the mean of our random variables that we're going to be using in our weight to our input to hidden layer weight. We also find that the standard deviation between the random values is going to be the hidden nodes to the power of negative 0.5. That's just a mathematical quirk which finds that's the fastest way to get to our values. And we put the dimensions, which will be the hidden nodes and the input nodes, of course. Similarly, we have here the weight of the hidden to the output nodes. And that's going to be a random number situated around 0. And it's going to be self.o nodes, which is our output nodes, all rooted 1 divided by root that. And that's obviously going to be the dimensions of the self.o nodes and self.h nodes. Okay, now that we've done that, let's try to understand what we're going to be doing here. So we get the inputs list. We change that to an array, a numpy array, so we can use the numpy functions. We transpose this. We then go to hidden inputs. We self.that, which basically means matrix multiply, with the inputs and the weight function that we defined it up here. Then we say the hidden outputs is all that activation function. So that will be the actual outputs, and the hidden inputs is the pre-activated system. Finally, we use the final inputs, which similarly to the first one will be numpy.dot, self.who, which is the weight function for the hidden to output layer. And then obviously you're going to multiply that by the hidden outputs. And the final outputs will basically be the activation function developed from the final inputs. Then we basically return the final outputs. And that's pretty much the neural network, without the training, mind you, done. So let's go ahead and go down to So let's go ahead and actually use this to query the network. Now, that actually initializes our neural network with the following factors, with the following parameters. The input nodes, we've got 3. We've got 3 output nodes, and we've just set our hidden nodes to be 15, and we got our learning rate. And mind you, the learning rate does have no effect right now. We'll actually use the learning rate in our next video when we're going to explain how to actually train our data. And finally, we call the neural network. Now that we have that, we want to just put in some dummy data and see if it actually gives us an output. And we see to have an error. We've got an error called neural network. Object has no attribute query. Okay, sorry. Query. That's what we called it. And let's see if that works. None. So it seems we might have put an error. Of course, we forgot to return our final outputs. Okay, now we've got these 3 values. So we put 0, 1, 0, and we get these 3 values. Now you might be asking, what the hell? What the hell is that? It's not this cool sci-fi based neural network which gets back does what we want it to do. Well, we haven't actually trained our system to work like that. And for any system to actually work, we need to actually train the data. Next week or next episode, we're actually going to explain how this can be trained, and we're going to use it to actually train our system. All right. Until then, I'll catch you later. And don't forget to hit the subscribe and like button. If anything didn't work for you, please mention it in the comments. If you had any questions setting up Python that you need some help in, I can try to help as much as I can. But other than that, yeah, subscribe, like, have a fun day.